Every time the bit shift left executes against this memory location, the state of the load bit, which you'll see in the instruction, is placed into bit 0. And each time you shift it, whatever you have formerly placed in bit 0 from the load bit, the load bit. So when a bit shift left executes against a register, a 16-bit register, and you can use a length greater than 16 bits. If you use 17, then it's going to shift 32 bits because it only works boundary to boundary in your memory locations. So if you shift 2 bits, it's going to use a 16-bit word. If you use 17 bits for your length, it's going to shift 32 bits. If you use 33 bits or 34 bits, then it's going to shift 3 words. So it only works boundary to boundary. So if we execute this shift register, or we execute a bit shift left instruction against this memory location, and it moves in a 1, and then the next time it moves in a 0, every time this shifts, the little blue smiley face is going to move to the next position, next position, next position. In the first lab for the bit shift left, we had you put the logic that you see here in, download it, go online into the remote run mode, open up the data file I1, lock it on top, open up data file B3 and lock it on top. The bit shift left instruction is, upon a false to true transition of the rung, controlled by a controlled data type at one of the memory locations, of which are tagged R6:0 through R6:15. That is, for the RSLogix500 10-point-IO processor, you have 16 control data type locations. Each of those locations uses 3 words in memory. If you're using a larger processor, then you might have R6:0 through R6:255. We had you use R6:10. Normally, instead of picking R6:0, I pick something else just to remind you that you don't have to start with 0. You could start with R6:15, and then the next time you need a control data type, use R6:4. You don't have to use them in sequence. The instruction, the bit shift left instruction, affects the state of all of the bits in the file. Remember, I said before, the first word of the file may be B315, but if you had a length greater than 16, it would be B315 and B316. So the size of the file in words is determined by the length in bits. In this case, the file is 1 word because the length is less than 16. We have a length of 10, so we're really only working with bits 0 through 9. And every time this shifts, it will shift what is in bit 9 into bit 10. But remember, our length, when it comes to other applications of this, does not include bit 10, 11, 12, 13, 14, and 15. We're only working with 0 through 9, but it shifts all 16. So we have a file, we have a length of bits in that word, and as you see, we're dealing with 0 through 9. So the BSL instruction, upon this false to true transition, will shift the states of all of the bits of this word to the left while copying the state of the bit address into bit 0 position. Now, I:0.5, you know, the 5th input in your input word, it's a 0, so nothing changed. If that had been a 1, meaning that that input was on, bit 0 now and B314 would be a 1, and then 1 through 9 would be zeros. It moved the state of bit 9 into 10. Since 9 was 0 and 10 was 0, moving a 0 to 0 doesn't change anything. So we're working with bits 0 through 9. Keep in mind, as I mentioned before, whenever you execute this instruction, a false to true transition of rung 0, whatever is in 0 through 9 will move to 1 through 10. So because the length is 10, we are actually unloading bit 9 into bit 10. On the occasion where the state of bit 10 is a 1, shifted into the unload position, which is length plus 1. Unload position for a bit shift left is always length plus 1. The unload bit will be set to 1. Now the unload bit, as you can see in rung 1, R6:10/UL, that's the unload bit. It will turn on output 3, just to indicate to you externally that a 1 was unloaded. So the unload bit always equals the state of the unload position, which in this case is the length plus 1, or bit 10. The idea of unloading is in concept only because you're not really unloading 10. You are indicating in the unload bit the state of 10. If we unloaded the 1 out of 10, then it wouldn't keep shifting to 11, 12, 13, 14, and 15, which it does. Now I show the unload bit here as a 1 just to demonstrate, but in reality, as you can see, B314/10 is a 0, so the unload bit would be off. So a better example here would have been to have shifted a 1 to position 9, then shifted it one more time into position 10 and had the unload bit come on, which it does in the lab. Now, I mentioned this several slides ago. The bit shift left instruction does not own the file that it affects through a shift. The state of each bit is designated in the designated file is subject to the results of any instruction in the logic that addresses that memory location, both to the bit level as well as the word level, and even to the file level, such as fill file and the copy instruction. The sole function of this instruction is just to shift the contents 1 bit position to the left on each follow-true transition, replacing the first bit with the state of the bit address as it shifts to the left. Keep in mind, you can have logic that executes a state change on any of these bits, 0 through 9, at any time in the program and for any reason. In other words, you could have a logic that turns on bit 4 of B314 under certain conditions. Well, it goes to 1, and on the next BSL, that 1 shifts to position 5. Or you could go in and clear or set to 0 any bit position with no regard to the BSL at all. Very, very versatile instruction, but always keep in mind, just because you chose B3:14, 15, whatever address you picked, doesn't mean that you own it with that bit shift left instruction. The applications are endless. Okay, let's step through this one step at a time. You've got your logic entered, downloaded, you're in the run mode, you opened up data file I1, locked it on top, reshaped it, opened up data file B3, locked it on top and reshaped it, so you can easily watch the bits. You basically want to watch input 5 in the input file, and you want to watch the first 10 bits in B315. So while observing bit 0 of B315, switch on input 0 to make rung 0 go true. Did bit 0 of B315 change states? No. What is the address and present value of the bit address in the BSL instruction? 0, because switch 5 is in the opposition. Now, with input 0 off, meaning that rung 0 is false, and observing bit 0, switch on input 5 to the on position. Did any bits in either file change state? Yes. If so, which address? Input 5 did. It went from 0 to 1, or from the off to the on state. Now, leaving switch 5 in the on position, switch on input 0. Did any of the bits in B315 change state? Yep. Which bits? B30. You loaded a 1, or the state of input 5, into the first bit of the file, B315, or bit 0. Switch input 0 off. The question is now, did the bit in B315 change state when you toggled input 0 on, or when you toggled it off? On, because the BSL and the BSR execute on a false to true transition. The rung went true when you turn on input 0. Okay, at this point we want you to do something else. While keeping track of how many false to true transitions it took to get 1 to the 10th position, bit 9, I want you to flip input 5 off and then toggle input 0 on and off until the 1 has shifted to the 10th position, or bit 9. How many false to true rung transitions? 9. 10 if you count the first one that was already done in an earlier step before step 7. So 10 is the correct answer if you were including the first one you did back in an earlier step. Otherwise, 9 additional false to true transitions. Toggle input 0 one more time. Where did the bit shift to next? To the next bit position to the left, the 11th position, or bit 10. What else happened in the logic? A state of 1 shifted into the unload position, which remember is the length plus 1. So the unload bit is now on, which made the rung true to turn on output 3. Now toggle input 0 once more. Where did the bit shift to? To the next bit position to the left, the 12th position, or bit 11. Did the unload bit stay on? No. It didn't stay on because you shifted a 0 into the unload position. The unload bit always matches the state of the unload position. Toggle input 0 until it reaches bit 15. Then stop, and while watching the bit, toggle input 0 on and off once. Where did the bit shift to? It shifted into bit space, infinity, and beyond. It just ceased to exist. Sometimes we call it the bottomless bit bucket. There's infinity number of bits out there for you to use, and if you keep dumping them into space, it just keeps adding. So every shift register that shifts a bit out the end of its boundary shifts it into bit space. Now we want you to toggle input 0 10 times, each time with input 5 in an alternate state. This should give you an alternating bit pattern that you see here in B315. You could go in and turn on 1, 3, 5, 7, and 9, change the states to 1 directly from your keyboard. However, it's better to actually exercise the logic. Then we want you to switch input 5 off, toggle input 0 while watching the indicator output 3 as each one shifts through the word. Shift the bits until all of the 1 bits are past bit the 10th position. When does the unload bit change to the on state? Every time a 1 shifts into the unload position, length plus 1. So it's real important to remember that it changes to 1 when it shifts into the unload position. So the unload bit has to see a transition. In other words, for the unload bit to come on, it has to see a transition of the unload bit position. When does the unload bit change to the off state? Every time a 0 shifts into the unload position, length plus 1. Just like the 1, or I should say the unload position, which is length plus 1, will only turn on the unload bit when it sees a 1 shift into that position, and it will change it back to a 0 when it sees a 0 shift into the unload position. Okay, from your keyboard, toggle the state of bit 7 to 1. All the bits 0 through 10 should be 0 with the exception of bit 7. Not the 7th position, but bit 7 that you just changed directly from your keyboard. Step the 1 through to bit 10. Did the unload bit behave the same regardless of how the 1 got into the memory word between bit 0 to 9? In other words, you directly typed it in from your keyboard. Did that in any way affect the final result of when the 1 shifted into the unload position? Yes, the instruction shifts and unloads not knowing where. The question was, I messed the question up. Did the unload bit behave the same regardless of how the 1 got in the memory word? Yes, it behaves the same. This instruction shifts and unloads not knowing where the bits originate from. Which means that you can use logic to manipulate the bits in the register that you are shifting with other logic. So it doesn't matter how you change the bits shift. B315 is not a shift register. It is simply a 16-bit memory location identified as B3:15. It's the 16th word in a binary array. However, by way of the BSL instruction, the bit shift left, you are manipulating those bits every time you execute the BSL against B315. So here you see a rung. I show no memory locations for those instructions. But when that rung is true, that would turn on B3 word 15 bit 7. That's how bit 7 could go to the on or the off state, because remember, an OTE instruction has a false and a true execution. So technically this rung of logic would control the state of bit 7. If the rung's true, bit 7 is going to be on. If the rung's false, bit 7 is going to be off. So be really careful. If you want to affect it one time, you need to use an OSR instruction, one shot rising, with everything that is a temporary state to the left of the one shot rising. Enough said. Okay, from your keyboard, change bit 13 to 1 and shift it out of the word, meaning out through bit 15. Set bit 10 to 1. Did the unload bit come on? No. Well, if 10 is the unload position, why didn't it come on? Because the unload bit is set to 1 when a 1 is shifted in. It has to see it go from 0 to 1 to set it to 1. It has to see it go from 1 to 0 to set it to 0. What can you say about all of the positions above the bit that represents the last position of the length in a BSL with the length less than 16? With the exception of the unload bit, they are of none effect. They have no effect on anything. Change the length of the bit shift left to 16. Shift a 1 through the word while watching bit 0 of B316, which is the next highest word in the B3 data table file above B315. What happened when the 1 shifted left from bit 15, which is the 16th position of B315, bit 15? It went into bit space, disappeared, nothing happened. Change the length of the BSL to 17, which is one word plus 1 bit. Shift a 1 through the word while watching bit 0 of B316, again, which is the next highest word in the B3 data table file. What happened when the 1 shifted left from bit 15 of B315? It shifted into bit 0 of the next highest word, B316. What happens when you increase the length beyond 16 bits? The file includes any 16-bit words needed to encompass the length in bits. Length of 33 requires 3 words, even though it only shifts through 33 plus the unload bit of the 48 bits, and the bits shift to the end of the 3-word boundary. Now, you change the length of the BSL instruction to 33. Stretch the B3 data table file display to include B3 15, 16, 17. Then, shift a 1 through the word while watching bit 0 of B3 17, which is the next highest word in B3 data table, above B3 16, which was the next highest word above B3 15. What happened when the 1 shifted left from bit 15 of B3 16? It shifted into bit 0 of the next word up, B3 17. Change the length of the bit shift left to 272. Press and release input 0. Well, toggle input 0. What happened? Everything shifted. 272 bits shifted. Now, you couldn't see it because when you're shifting zeros, you don't see anything happening. Take my word for it. 272 bits shifted. Now change the length of the BSL to 273. One more bit. Press and release input 0. What happened? Faulted. You got the old red winky. On your processor, you notice that the fault light was winking at you. I had you actually go through the exercise of dropping down the list next to faulted and select go to error. Read the fault description. Use the help file to find a description of the major fault. And basically it tells you right there on the screen, instruction cross data file boundaries. In other words, you try to shift a bit out of the B3 file into T4. No can do. A length of 272 is the number of bits starting at bit 0 of variable B315 and going to bit 15 of B331, the last word in the data file B3. Now, if you weren't using the RSLogix500, which has a fixed length of 32 words for B3, then your processor didn't fault. You would have to increase the number of bits. Instead of 272, you would have to go from B315 bit 0 all the way probably to word 255 bit 15, and then go one more to get it to fault. If you try to shift a bit across the boundary separating two data files, not two words, but two data files, you'll fault the processor. Clear the fault. You went back to the run mode and changed the length back to 17. Did the processor fault when you changed the length to 273, or did it fault when the processor tried to execute the shift? When the processor executed an instruction that violated a data table boundary. Having an illegal length in there doesn't fault the processor, but when you try to execute it and actually move the data into forbidden territory, that's going to fault the processor. If the length is set to 272, how many bits does the bit shift left shift on each execution? Let's say 272. Otherwise, you would put in a different number. Shifts 272 bits. If you were to set the length to 0, what results would you expect? 0 bits shifted. Now, I had you try a length of 0 to see how close you called it, and you saw nothing shifted. Now, you have to have a 1 in there to see whether it shifts or not. Okay, speaking of the length, which is an integer, 16-bit integer, R6:10 dot length, LEN, which is an integer register in the structure of a controlled data type, known as a predefined data type. Add the additional rung shown in the next illustration, shift a 1 to bit 9, and then stop. Okay, so as you can see there, the current length is 10. If you execute this wrong, you're going to put a 12 in the length. So the bit is set at bit 9, so the next shift ought to go to the unload position and turn on the unload bit. Okay, toggle input 1 on then off. Did the length of the bit shift left instruction change? Yes, it changed to 12. Toggle input 0 on and off, which executes the shift register. You would have expected the unload bit to be on if you had not changed the length of the BSL. Is that true or false? That's true. If you had not changed the length, then the next shift would have went to the unload position, turn the bit on. But when you change the length, the unload position is now 12 plus 1, the 13th position. Shift the bit through bit 11 to energize output 3. Shift another bit to bit 9 and stop. Now, change N70 to 8 and then toggle input 1. Did the unload energize output 3? No. Why not? No shift into the unload position occurred. Just because you see, even if you see the right value in the unload position, if it wasn't shifted into there, in other words, if it didn't move into there when the instruction was being executed, the BSL, then there's nothing to unload, even if the position is now 1.